Hello and welcome to today's Happy Maths Hour.
I want to introduce you first to this wonderful maths site, which I've just discovered, called Mathagon. Okay, it's absolutely the best website for mathematical school activities. It has got so much, you'll be amazed. So it's got a very simple name, Mathagon, and it's free. I do recommend it. And it's called A Textbook of the Future. In fact, it could be a complete school course. It's got so much of the basic work that we all teach in school, and in addition, it's got a lot of enrichment material. What you're seeing now is the Facebook page for Mathagon, and I'll leave you to, there it is, I'll leave you to discover it, to explore it, to make use of it for yourselves. And now we're going to do some work on circles, but amongst other things. And today the thread that will run through our chat is three numbers, just simply three numbers, and a lot of just adding two numbers to get the other one, and sometimes combining the two numbers in another way to get the third. So here we go. Now, this game, Check It, we're going to talk about it quite a bit. And it's a game that Caroline and I love because it can be changed, and variations can be, well, there are endless variations, aren't there, Caroline?
Yes, it's content free. You can use any content within it to play the game.
And this version is for really small children. You can play this even before they can write down the numbers, the digits. Have you played this with very tiny children, Caroline?
I have with dots. Yes, I have. I've played it with my little friend Holly, and it works beautifully because the dots just make so much sense.
Yes. And what you can do is to have some stones or counters and put them on the board. And you see, the rule is that the ovals, or ellipses, I prefer to call them, at the vertices of the triangle, and the two numbers in there added together give you the number in the middle. You can actually show that by separating, if you're doing it with the counters or stones, you can separate them into a 2 and a 3, and a 6 and a 3 for the number that goes in the rectangle at the bottom to make 9. And then your little children can count the numbers, the number of pebbles or whatever they are. You play this game by taking it in turns to put counters in the boxes, and you've got to follow this rule. So more about the rules as we go on, and there, of course, is the solution for this version. So we're bringing this to you from the Global Teacher Empowerment Network, and we're offering new skills, new hopes, and new horizons for teachers and learners everywhere. So here is another version of this game, and just think you might like to do a little bit of mental arithmetic. What should replace the question marks there?
I'm going to have a go, Toni. So 88 plus 100, take away 1. So 188, 100 minus 1, 187. There you go. I've got that one. Now the one at the bottom, same thing. 55 plus 100 is 155. Take away 1, 154. And on the left-hand side, I can do 88 plus 50. So that's 138, and then add another 5. So it's actually more than 50. So that's 143.
There it is, and there are your answers. So you can set it as a puzzle and say, well, can you fill them in? Or you can take it in turns to fill them in. And if you get it right, you get a point. If you don't, you lose a point or something like that. You can actually invent your own ways of scoring. Now, here's a variation. Can you see the difference here? Numbers in the middle of the edges are the total of the numbers at the vertices again. And as before, we can find the number on the bottom very easily.
Oh, but we've got the vertex is missing. Oh, okay.
Oh, yes. So
oh. Okay, so we're adding again, I'm assuming.
So it's 99 plus what number? Is 333.
Okay, right. Well, let's get the one on the bottom. So that's 99 plus 66, 166 minus 1. So that's that, but it doesn't give us any other clues. All right, so 333 minus 99. All right, so it's 333 minus 100 is 233, but we've only taken away 99, so it's 234. And then now that we got 234, we can add that to 66. So 234 plus 6, 240. Oh, it's 300.
It is. There's the answer.
Okay.
So you can begin to see that we started with just the pebbles, not even any numbers written in this form. And then we went on to just 2-digit numbers. And now not only we're doing 3-digit numbers, but we're doing the puzzle the other way round. It's sometimes called a standing on its head puzzle or an inverse puzzle. And again, you score in the same way. And now up in the top corner there's another puzzle, but now you can see you can go up to 4 digits or even 5 digits. And
yeah, those are big numbers.
So you can then, if you're doing this with children, as they get familiar with bigger numbers, they really need to be able to do this sort of addition and multiplication. You're going to give, number sense, practicing mental arithmetic, and making it in a playful and a really fun way.
I was just thinking, going back to the last one we've just done, it would be interesting if you comment in the comments, and the ones I worked out, if you might have used a different method. So it would be really interesting to hear all the different methods that different people have used. That's all. Now I'm itching to get. I saw fractions. Now,
well, since you suggested we go back to this one, Caroline. Yeah. I mean, the one up at the top right and the smallest one there. I rather like it because it's 9,999, and you can use your method that you used with 99, but of course it's a much bigger number, isn't it?
But it's still only one different to 10,000, and that's a really nice. But when you realize that's very powerful. Yeah. You've also got 9,999 plus 1,111. So that's a nice little...
Yeah. So there's actually quite a lot of little subtleties to make the number. We haven't given them difficult numbers to add and subtract. We've built in some of the ideas which teach you some shortcuts to doing mental arithmetic. So now, Caroline, you wanted the fractions.
Okay, right. Now, once I actually got how to add fractions, I just really love adding fractions. always had love for adding fractions. So we've got to be comparing apples with apples. We can't be saying 3/5. We can't say 3/5 plus a half. You can't add a 3 in the 1. So a very, very simple way of doing it is just saying on the denominator is just 2 times 5. And then you could do that. So you can put them both over 10. So 3/5 is 6 over 10. And 1/2 is 5 over 10. So 3 plus, I don't know if I'm getting this right, 3 plus 5. So it'd be 8 over 10, which is 4/5. On that one, I think.
What? 6 tenths and 5 tenths is 11 tenths, Caroline. 11
well,
tenths.
So I got that wrong then. So it's 1 and a tenth.
Okay. I'd have accepted 11 tenths quite happily.
In my class, I've got a thing at the top. Spot the mistake. And it's the kids' responsibility to spot all my deliberate mistakes. So, and then I demonstrate very beautifully how you use your mistakes to learn from them. Beautifully, of course, because I always do everything beautifully. So 3/5 plus 1/3. See if I can do this without. Okay, so let's go for this 3 times 5. So we're going to make it over everything over 15. So that means I've got with the 3 times 5 becomes 15. So that's 1 times 5. That's 5. Okay, I'm going to make a mental note. And on the other hand, it's 3 times 3. So that's 9, I think. So that would be 5 plus 9 is 14 over 15. 14,
I think
15?
that's what it is. I think that's what it is.
Okay,
yeah.
that's what I've. And as I said, comment if you've got a different way of working it out. Please comment. So this last one, okay, we can just again say, put it all over 6. So that'll be 2 plus 3, which is 5, 5, 6. 5, 6. That's hard to say. 5, 6.
There we go. Okay.
Oh, thank you.
Now, of course, it was right. Now, of course, what I didn't put on this slide, but there's a lovely fraction wall, and you could use that as a method where you build up the layers of the fraction wall, and you have a unit, and then you have it split into, and then you can see why Caroline's multiplying the two numbers in the denominator in order to, as she said, compare apples with apples. And but players agree the rules at the start, and check it can be played for whole numbers, and we've just seen for fractions, or because it also can be played with integers, so you can have some positive and negative numbers. And we're going to see in a few minutes how exponents or powers, it can be used there, or algebraic expressions, or even words.
And decimals, and also percentages.
Absolutely. So there's endless possibilities now.
And algebra.
Yeah. So what we've been doing is adding. But why not do multiplication?
Well, it's much easier to multiply fractions and add them.
Yes. So there's the answers already given for that. Check it. So to just recap on the rules that we play, but you can vary the rules. That's the whole point. In other words, you can give different numbers of points if you agree on a different scoring system. And this game can be played with 2 teams, in which case the teams have to usually have an agreement on, they can have time to consult and agree on what to put where. Or you can play with individuals. It's best as a 2-player game, but and when you play it with 2 players, you take it in turns to fill a box. So you start, we've been showing you the version of the game where you start with 3 numbers or whatever given in the boxes and 3 blanks. So you take it in turns, and one set of rules is just to get a negative point or get a point against you if you make a mistake. So you keep, keep on the right side as long as you don't make a mistake. But when you make a mistake, you get a point against you. And of course, that's the one who's got the least negative points is the person who wins. But you can do it the other way around, of course. Every time you get one right,
you can get positive. You can get positive points if you get it right. Yeah. But if you actually make a mistake, you can have points taken away, which gives the incentive to the other person to actually check everything you're doing.
That's true. That's true. And some of these games we actually, where they're a little bit harder to do, we build in this idea of checking each other's and giving a certain time for that. And if you don't spot a mistake, the teacher doesn't point it out, but if the opposition doesn't spot the mistake, then you get away with it.
Yeah, that's right. Yeah.
Yes, yeah. So
it's like, was like the other game that we played, the square it. If a person could make a square, but if they don't spot that they've made it a square, then you could still go ahead and win, and they don't get to win unless they actually highlight the fact that they've made a square.
that's to keep everybody on their toes, really.
Yeah.
And it makes it a bit more challenging. So you can start with a blank check it, make it up as you go along. Okay, so you decide which operations. You might decide on addition, you might decide on multiplication, you might even decide on some other operation, way of combining. It's always a matter of combining two of the numbers to get the third. Okay,
this can be very challenging, because especially if you just start off with putting one in one of the rectangles, then you've got to make sure, or if you even start with all the rectangles, that could be the game where you must fill all the rectangles, and then it's got to be possible to do the operations to get it right. And so that's quite, it takes you a lot further down the line. You have to look much further ahead, and
now you see in this
nice
game,
and challenging.
In this game, what we've got is 6 empty boxes. Okay, so with 2 teams or 2 players, each fills 3 boxes. And so it's easy for the first person to go, and easy probably for the second. And then you have to be a bit more careful, because here, if you start putting in the third number, you might be doing it in such a way as it's impossible to complete the whole set of 6.
Yeah.
So you have to have a plan in your mind about how it could be filled in. And of course, at the early stage, there's lots of different ways it can be filled in with a set of agreed rules. So you take it in turns. So with the third number, you have to be able to say, if you're challenged, how you would complete it with 6 numbers. And then as you go on, it becomes harder to put the next number in. So you win a point if you put a number in successfully. You lose a point if you do something that put a number or expression in that's wrong.
That's impossible.
And
yes, you can either make an error, or you can put in a number that is correct up till that point, but makes it impossible to solve it.
Indeed. And then also, you can challenge the other side. You can say, I don't think you could actually finish the frames with that number. I don't believe it. And if they show you, if you make a challenge and they show you, well, actually, you're wrong, it can be done, then you lose a point for...
If you make an incorrect challenge.
Indeed. For a correct challenge, of course, you win a point.
You win a point,
yeah. It can be quite a challenging game and a lot of fun. But what I'm meaning to say is it can be a game that makes you think very hard about what you're doing. So make it up as you go along is tell your own check it is actually lovely. Actually, it's a really nice game. So you take turns to fill one of the boxes, always making sure that it's possible to complete a set of 6 entries. And if challenged, a player must show they can find all numbers to complete all 6 entries. And you check each entry before moving on to the next one. And players score a point if they make 3 correct entries and lose a point if they make a mistake. And it's actually quite a good game for 2 pairs, to have a game with 4 people, but a pair playing against another pair, because then the pair can consult and check things together.
Yeah, nice collaboration.
It's really nice when you do it that way. So there are different possibilities. Everyone plays the game and they suggest numbers to be put in the boxes. Okay, now here's the next thing. This one is, can you see the powers? We've got a 3 squared on the left bottom, a 7 squared and 2 squared. But here, what you have is prime numbers. 2, 3, 5, and 7 are all prime numbers. It means they haven't got any factors. So you break the numbers down into prime factors. And so the numbers in the rectangles are numbers that divide into both of the numbers at the at the vertices in the ellipses. So clearly 2 divide. If you're looking at the left-hand one here, 2 divides into that and 2 divides into that, but 2 squared isn't a common divisor.
Right. So what do? You write the 2.
Well, that
so
we've got.
You're writing the
you
common.
do that. So
you're writing the common divisors into the rectangles.
Indeed. So you can see it now. On the right-hand side, only 3 divides into both of those 2 numbers at the vertices.
Right. Okay. Yeah.
And at the bottom, 3 times 7 does, but
So
not 3 squared and not 7 squared.
Yeah. Yeah.
And on the left, 2 times 3. 7 doesn't and 5 don't divide into both of them. They divide into one or the other. So again, you can play it with 2 pairs or 2 teams. And here you start with a blank frame. Each creates a puzzle with 6 entries, as in this example. Then they draw it with 3 entries missing and give that to the other team. And each team solves the puzzle created by their opponents. And then they check all the solutions. That's another way of playing it.
Wow, that it wouldn't. I don't know if it would have ever occurred to me, but it certainly hadn't occurred to me to do that with Check It. So that is very powerful. And this way, it's just a game. It's lovely.
Well, I have to say, I'm sorry to those of you who are not actually teachers, because this is quite a lot about teaching, isn't it, Caroline? But
well, I suppose so. But I mean, your children will be doing it, and
you could do it at home.
Way, exactly. This way, you can play the game at home, and if you aren't sure of the maths, they can do the maths for you, but you can still play the game together. It's
well. So this is actually giving them practice. Because but they don't feel that it's sort of just boring old drill and just doing lots of examples that are the same so that they remember it, but they are doing lots of examples that are the same. And there's nothing better than making up your own puzzle to really understand what you're doing. And here I love this version actually, where it's 2 groups playing each other, and they each make up a puzzle which they know works and they've checked, and then they just give 3 of the fill in 3 of the boxes, and the other team has to fill in the other 3. They swap them over. And,
okay, they're in a puzzle, and it's got to work.
Yes, yes. And yeah, it's a nice way to do it. But it was even more versatile. What about this?
That's nothing to do with maths, Tony. Those are words.
Well, yes, it's just a word
going
puzzle.
On here?
Yes.
Okay.
Well, here the rule is that adjacent words must have 2 letters in common. So tiger and goose have a G and an E in common. Okay. And rat and ants have got an A and a T in common.
So we've got to find a word that has 2 letters in common with goose and ant.
No, so there must be at least one in all 3 words on each edge. So for example, on the bottom left, it's got to have at least one of the letters A and T in it, because it has got to be at least one all the way along the bottom.
At least one. Okay,
of A and T.
It's got to have A or N or T.
Yes. And for example, you could have Nat, G-N-A-T, in that bottom one, because it would have a G in common with
goose.
Goose. Oh, wait a minute. It's got to have 2 in, Nat wouldn't do because it has to have two in common with
But that's
goose.
what I was asking you. That is it one or two? Do I have to have two?
It's two with its neighbours and one along the
Oh,
whole edge.
what about goat?
That works. Okay.
Oh,
So
one along the whole edge. Okay.
So
So
along
and
the
then,
tiger goose edge, it's a G all the way down. And there's two letters in common with goat and goose. Okay. But there's only one that runs all the way down, the G. And there's two in common between goose and tiger. It's a little confusing when you first meet it. So the way it works is there are other words that you could put here. And of course you don't need to stick with living, breathing creatures. You know, all of these are living, breathing creatures. I mean, there are insects, and there's tadpole lives in water, and the others are land animals. Well, the goose likes water too, but it doesn't live underwater. But of course, you make it easier by saying, well, you can have any word about anything. You can have tree or box or table, or, you know, coat or anything you like. So it would be much easier if when I made this up, I thought, I'm going to make myself a rule. They're all going to be living, breathing creatures. Okay. But you don't have to be as strict as that. And they're just so much fun to make up. You know, you don't have to make it a sort of a competitive game. You know, you can just sit around and just make one up. You know, between you, who can think of something here?
It can be a collaboration. It doesn't have to be a competition at all. It'd be like, okay, how can we meet these specifications and create it?
Did you ever watch the TV game Call My Bluff, Caroline?
I did. Yes.
It was a word game, and the way it was is each challenge. Of course, you had the people, you know, the people competing, but each challenge was a word that very few people have heard of, a really obscure word. Okay.
Oh, and then they had to work out whether is that a real word or not.
No, they were all real words, but so they were all in the dictionary. Right. But then you were given 4 definitions. Right. And you had to decide which of the 4 was the correct definition.
Right.
Well, we used to play this at Christmas or at home with my parents and my children, okay? And so anybody else who was around. And we would go into 2 separate rooms with dictionaries, and we would make up our own. So people would just having fun making it up. They would find 5 words in the dictionary, okay, that were really difficult words that nobody had ever heard. And then they'd make up definitions for those words. And then, having got their words and their definitions written on cards so that it was all pre-prepared, we all came together and we took it in turns. And we had 4 people giving the 4 definitions, and each of us trying to convince the team that my definition was the right one.
Right. Yeah.
And if the team pick out the right definition, then they score a point. And if they can't pick it out, they pick one of the wrong definitions. And I mean, what you manage to do is to make some of these definitions really funny, you know, and then it is hilarious. But my point was, it's as much fun to make up the puzzle as it is to actually solve it.
And a huge amount of learning goes on in the process. I mean, especially, this puzzle, you've actually got to, I love the definition ideas as well, because you'll always remember the definition of those words. And and this one, you've really got to think about it to find words that work.
Yeah. Okay, so you make up your own puzzles. You can give another person the puzzle with 3 words missing. You can take it in turn to fill in the boxes, always making sure that it's possible to complete it. And if challenge players must show they can find words to complete all 6 entries, and you can set a time limit if the players agree at the start that they can't. But actually, it's quite fun if you take, even several days, even. You know what I mean? If you sort of have this on the fridge, and you can actually, you can't immediately think of a word. You just, you think of one and then you go and fill it in when you can. Now, this is an algebra game, and we won't dwell on this, but this is another version where x squared minus 1 at the top is x minus 1 times x plus 1. Okay, and in the box in the middle, you've got to have a common factor. And so x squared plus 5x plus 4 is x plus 4 times x plus 1. The common factor on the ABD line on the left is x plus 1 is a factor.
Oh, it's just a factor.
Yes,
right.
And on the ACF line, x minus 1 is a factor. And
ACF x minus 1, okay.
X plus 4 times x plus 1.
Hold on.
X plus 4 times x plus 3. Yes, x plus 4 is a factor along the DEF line. Anyway, if you don't know the algebra,
where is that? Where do you say that? Where do you write that?
On the top left-hand side, you see, you start with that, and you've got to fill in the 3 missing ones. And each entry is a quadratic expression, okay? And there must be a common factor in all 3 expressions on each edge.
Yeah, I think that one requires some more thought before I would be confident doing that.
I'll remind you that you can make up your own and have fun, and it can be a word game, and it can be tough maths for some, like algebra, or it can be very easy maths, as we showed you at the beginning.
But as I always say, Toni, if you find it's too hard, then start with a simpler version. Start with a simple example and build up towards the more difficult ones, and that way you learn the more difficult ones. Yeah.
So get some plates and push them together, and you can always do that. It's always possible, so they all touch each other in a chain or a necklace. Okay, so I've got a necklace with beads on here, and they're all the same size, but you've got plates, there are circles of different sizes, and what you see is, given a collection of discs, circles, they can be arranged to touch each other. And then you join the centers, okay? And on the right, you've got 5 circles or discs, and you have joined the centers, and you can see you've got a pentagon. Now, does it work the other way around? Given a polygon, can you find circles with centers at the vertices of the polygon, with each circle just kissing?
That sounds pretty challenging.
Touching both its neighbors. Now, because you can push the plates together to make the chain, however many plates you've got, you might think you can start with the polygon and draw circles centered at the vertices. Can you always do it? That's the question. So this is called the Polycircles Puzzle. And again, the idea is along each edge, there's going to be 2 radii, and they're going to be added up to make the length along that edge. So there's going to be 2 numbers that are added up to get the 3rd number. So if it's a regular one, like you see at the top there, these a regular, an equilateral triangle or a square or a regular pentagon, you can always do it, because you just have the circles all the same. And that's easy. But what happens if the circles are different sizes? Now, on the right, with the red, blue, and green circle, you can see that works, can't you? And so if the red circle has radius 4, and the green circle, little one, has got radius 1, and the blue circle has got radius 2, you can see by adding the numbers along the edges, 4 and 1 make 5 for the length of the triangle, one edge of the triangle, and the other 2 edges are 6 and 3. So sometimes we can have solutions and sort of challenges. Can you find a method for develop a method for finding solutions? And can you start with any triangle? Can you always find a solution? And actually, the answer is yes, you can, and that's for triangles. And then you go to bigger polygons. We saw it. We saw it with the plates and a pentagon. And here we just want to flag up that if you haven't ever used GeoGebra, you might enjoy it. It's free. It can be used on a computer or any device, really, including a phone. You can download it. There is lots of help to get to learn to use it. It's very powerful software. It's been around for it's always been free. It's been around now for about at least 40 years. I mean, it was one of the early packages, very early, when we had very, very simple computers. And it's because there's a big community that contribute to it. It's one of these open source software where lots and lots of people have added to it and made suggestions, and it's absolutely brilliant. So now you can start off with an equilateral triangle, for example, where you know it works, and you've got your 3 circles, and then GeoGebra is what we call dynamic geometry, dynamic software, which means dynamic means it's changing. You can change it. So you
can experiment with it and move things around. You can
drag one of the points with certain conditions that have got to hold, and the whole diagram moves as you drag one of the points, and it changes, and it keeps following the same rules. So if your rule was kissing circles, okay, you know what I mean, they've got to touch and not overlap, then it would keep that rule, and you could see how it worked for different triangles.
Nice.
It's really nice. Okay, so there's some examples. So we have got there a quadrilateral, so we've got in each of those 2 diagrams, you've got 4 red circles, but now the circles of different sizes.
Yeah.
We're joining up the centers, and in each case, we've got a quadrilateral. In the case on the left-hand side, we have got a dotted blue circle that just touches each of the edges of the quadrilateral and just touches them. So it's what we call an inscribed circle. And I think that's pretty. I think we should have this thought experiment. Now, you imagine Caroline with one of her sausage-shaped balloons, all right?
Like the modelling balloons. If you ever had a dog made for you,
poking through, okay, here, right? And into the center of this quadrilateral, and then expanding. And as it expands, it's a blue balloon, and as it just touches one edge, it just touches all edges. You can do that experiment.
Then I asked, can we do that as well with the one on the right? And because I couldn't see how, but actually I can see how, because if the balloon is right in the center, then those 2 edges, it almost looks like a triangle, doesn't it? But where it touches, where the balloon touches, those 2 edges it's almost straight, would be very close to each other. They wouldn't be anywhere near the center of those 2 edges. They'd be very close to the vertex.
That's right.
That's the key that I couldn't
yes.
see it until I realized, it's not the midpoints. Then the point where they're touching, the tangents of that circle, they're not the midpoints of those edges of those polygons. They don't wherever. Yeah,
no, they don't. And even on the left, the blue circle doesn't touch all the edges at the midpoint.
That's right, very much so. And so I suppose, but for a regular polygon, it would, I'm guessing.
Yes, it would if it was regular. So what I've drawn on the right to make it even more complicated is in each of the red circles, right, we have got 3 circles, 3 green circles, and so we've got 12 of them all together in a chain.
So there's 3 in every circle. They're not going anywhere near the center of the circle. This is not about the center of these circles. The polygon is formed. I'm just thinking it through as I'm looking at it. The polygon is formed by joining the center of those 4 circles, but then these other little circles are just, it's just the necklace.
Well, we could have
as long as they touch.
We could have a dodecagon, Caroline. We could have
we
12.
would if we had, because there's 12 of them, because 3 times 4, that's 12. So yeah, that's a dodecagon, which is 2 and 10. Yeah.
We could actually draw there, joining the centers of the, of each pair of green circles, we would get a 12-sided polygon. But I didn't draw it in because it would have just looked hard to see it. It would have been, I think we can imagine it. But what I would like to say is that what we have got is what we call polycircles, a necklace now, like my green beads here, but they're all different sizes.
But what I'm fascinated by is the fact that my camera is working. I'm very pleased to say, but what I'm fascinated by is that they go round, but they're not. I'm not necessarily going to draw a 12 edge shape, but it's got a little bit that goes inwards. It doesn't have to be a convex.
What Caroline is pointing out, and you can see it by looking at here, what she's pointing out is that these circles here, if you join the centers, the polygon won't be convex, all right? So some of the angles, it will sort of go in there. Some of the angles will be more than 180 degrees inside. It's not a convex polygon has all the angles less than 180 degrees inside, the interior angles. So I think that's what Caroline's, isn't that what you're looking at, Caroline?
Yes, because I was surprised to see it inside, especially inside the little circle.
Yeah, inside this one, yes, that's right. But inside, you can imagine joining the centers.
Tony.
You can imagine joining the centers, and then there it takes a little dip in towards the sort of middle of this dodecagon, rather than going out that way.
Yeah.
Okay, so I think it's rather a nice topic here. Now look at the rectangle. We've got 2 quadrilaterals above.
They're not touching. Those circles aren't touching.
It's impossible because
so it's all quadrilaterals then.
It doesn't work for all quadrilaterals. You can't find the polycircles for all quadrilaterals. And so what you can, the nice thing about it is that if you can find the polycircles, you will have an inscribed circle as well. So you can do the balloon test.
So if it works, you can do the balloon test. You'll get a balloon that will touch all the edges.
Yes.
But if it doesn't work, oh my goodness.
Yeah, isn't that nice?
And that's a really nice way of seeing it.
It's not beyond school maths to prove it, but it's really beyond we haven't got time.
Well, it's not.
So what I want to show you in the last few minutes is another of these ideas where you just have 3 points to start with. That's all you have, 3 points. And what you then have to do is you're given that they are the midpoints of a bigger triangle. So you make a red triangle there. But what you're trying to produce is a bigger triangle with the points that you started with at the midpoints of its edges. So again,
so you've got to find, so the challenge is to find the triangle that matches where those 3 points are the midpoints of a larger triangle. So
The
it's
edges
not,
of a larger triangle.
they're not the vertices of it. They are the midpoints of the edges
Yes.
of the larger triangle. So this is a method by which you can do that, because I would have never imagined you could do that. You got 3 points. Well, how on earth are you supposed to work out the midpoints?
Well, there's all sorts of different ways, but we'll show you one in a minute. But again, you see, it's following the theme that Caroline and I have been talking about throughout the afternoon that started with check it. So the diagram on there with the black and red triangles is a little bit reminiscent of check it, isn't it? Not quite the same, but basically along each edge, we've got the 2 lengths of the edge is divided into 2 lengths, which add up to give the total length along that edge.
Yeah,
so
it is like check it, isn't it? Because
a bit like
you basically got the information about the location of the 3 midpoints.
Yeah. So it's
and
a
then
bit
so
like
you're building up the vertices from
so
it.
it's like a check it where you're given the what's in the rectangular boxes in the middle of the edges, and you've got to find the vertices.
Yeah.
So now when you join the midpoints of the edges of any triangle, so you start with ABC and then you have to find PQR. But you know that ABC are the midpoints of the edges of PQR. And what you can see is if you have that sort of relationship between these 2 triangles that we've been describing, then it will be divided up into 4 congruent smaller triangles. The red one in the middle being.
Okay, all right. So basically, 4 triangles that are just rotations of each other.
And what's more, PBCA is a parallelogram.
Yeah.
BQCA is another parallelogram, and ABCR is another.
It looks that last one looks almost like a rectangle, but it doesn't necessarily.
Well,
it doesn't have
ABC
to be.
is almost right angled, but
it doesn't have to be. It could be.
Doesn't.
It could be as skew if as you like.
So you can actually find this and solve this, but you can find PQR. I mean, the triangle PQR by construction. So you're given the 3 points, which are A, B, and C. And then this is what you do. First 3 steps are shown in the picture there. So at first, what you've got is you've got to knowing that's the midpoint, then you draw C to that midpoint. Well, no, so you actually, you measure it. So you find that midpoint, another midpoint, a midpoint of a midpoint sort of thing, and you join C there, and then you extend it a bit further. So that's what you do. You join C through to there, and you extend it a bit further so that length and that length are equal. And then P is one of the points you need, because as you see, A, P, B, C is a parallelogram. And it
is going to be a parallelogram because you're starting at C, you're going through the midpoint of AB. Therefore, once the same length again, and that'll give you the final vertex of the parallelogram.
Indeed,
that's beautiful, Toni.
And actually, it is it's a parallelogram because the diagonals of a parallelogram bisect each other. So by making these 2 lines, CP and AB, cut each other in half, you force that to be a parallelogram.
And at the same time, you're really getting very familiar with the properties of a parallelogram.
Yes.
It'd be very hard to forget that the diagonals of a parallelogram bisect each other after constructing a triangle like this.
Indeed, that's right. So you've got you do the same to find Q, and you get ABQC is another parallelogram. And having done that, I'll come to the summary in a minute. Having done that, you now need to find R. So you do exactly the same thing again, and you've got A, B, C, R is another parallelogram. And bingo, it's done.
That is
pretty,
I would have never imagined, Toni. I mean, I know this has been centuries of people at enhancing each other's work, and some people just spending a lot of time in their life investigating this. But this is a sort of thing that discoveries that you can make in maths that are, well, other people have discovered it before you, but you talk about that you can make your own discoveries. Even it doesn't matter that people have made them before you. You can make your own discoveries, and there's a lot in there to discover.
Yeah. It just shows you how beautiful maths is, and it's one of my favorite. It's one of my favorite sort of little packages of mathematics, because you won't be surprised when I tell you that polycircles and triangle midpoints, if you do it algebraically, they are, you know the word, Caroline, isomorphic. They're actually the same problem.
The same problem, yeah.
In completely different context, and we often call that property in mathematics. They're both the same, but what they're in disguise, so you don't notice they're the same until you think about it a bit.
Nice.
Yeah, so that's something else. Now, the summary of what we've been doing, we had lots of check-its, lots of them for different we had 6 boxes to fill in, and it could be fractions, we could do it with algebra, we even did it with words. And
I think, Toni, it would also be great if you've got ideas of what you could do with Check-It. Could you put those in the comments? See what other ideas you might.
It would be lovely to share some more ideas. Yes, yeah. That would be lovely. And then we came on to our polycircles, and then the triangle midpoints, and there's some versions of triangle midpoints. And on the right there, we can do it with coordinates as well, but we haven't talked about it with the triangle midpoints with coordinates. We haven't done that this afternoon, but we could use it.
Yeah.
We could solve it with coordinates.
That'd be lovely.
And then you can do it with constructions, which we have done, and you can do it with algebra. And at the top there, a plus b equals 6, b plus c equals 4, and c plus a equals 8. We can do some algebra. And if we do polycircles with algebra, and if we do triangle midpoints with algebra, we see the algebra is absolutely identical.
And there's the isomorphism.
Isn't that nice?
Yeah, that was lovely. That was the very mathsy, but beautiful. I mean, it really shows. But it games and maths, and then I love the idea of constructing shapes without just with a ruler.
Now, we have everything here, from a very simple version of Check-It that you can play with 4 or 5-year-olds, to something now I'll throw out as a challenge for professional mathematicians. If you haven't seen this before, and you think yourself to be a really knowledgeable, good problem solver, professional mathematician, then just give it. This is a challenge for you. For what values of n, that's the number of edges of the polygon, is it possible to form the polycircles? For some values of n, it is, and for some values of n, it is not possible. We showed it wasn't possible for a rectangle, or rather, for some values of n, it's sometimes possible and sometimes not. So for a 4-sided polygon, it's sometimes possible and it's sometimes not. And under what conditions is it possible? And under what conditions is it not possible? So you
this
can
question
see
is not aimed at a parent who's here wanting help with their homework.
Oh, but it is aimed at somebody who's a computer scientist or an engineer, or who's quite good with maths and problem solving, because it's not difficult. It's just you have to think. You have to think hard, and you've got to be determined, and you'll probably find it.
Perseverance and determination.
Yeah. So this is what we call a low threshold or low entry point, high ceiling. It's a sort of activity that is versions of it, all connected with a lovely thread that runs through, from very small children to anybody, however much maths they know. If they haven't seen it before. If you've seen it before, of course you know. But if you haven't, you might like to have it. You might like to take up my challenge. Okay, and then the last little one to fill in is the pretty one, where we have got 12 circles in a chain. But is it true No, this is the same challenge, but you could start with a 12-sided polygon if you like. Can you do it? I've shown you with the green ones. You can for that particular polygon, but can you do it for all 12, all polygons with 12 edges? And generally not 4 or 12, but for any n, what's going on. So it's goodbye from us. A lot of lovely ideas.
Absolutely. You have definitely surpassed yourself, Toni. Thank you so much. And thank you everyone for joining us.
We hope you'll come and to Happy Massa next week.
And we got a heart. We got a love heart. Somebody loved it. Thank you. Thank you for joining us. For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.